So let's move on to the second speaker in this session. It's Professor Yuke Zhu from the University of Texas at Austin. He's an assistant professor in the computer science department where he directs the Robot Perception and Learning Lab. He's a core faculty member at Texas Robotics, the Machine Learning Lab, and the Center for Perceptual Systems. He also co-leads the Generalist Embodied Agent Research, called GEAR, lab at NVIDIA, which builds foundational models for embodied agents in virtual and physical worlds, particularly for humanoid robots. Yuke focuses on developing intelligent algorithms for generalist robots and embodied agents to reason about and interact with the real world. His research spans robotics, computer vision, and machine learning. Yuke received his MS and PhD from Stanford University and has won various awards and nominations, including Best Paper Awards at ICRA in 2019 and 2024, the Outstanding Learning Paper Award at ICRA 2022, and the Outstanding Paper Award at NeurIPS in 2022. He has received the NSF Career Award, as well as faculty awards from Amazon, JP Morgan, and Sony Research. The title of his talk today is Pathway to Generalist Robot Autonomy, a Data-Centric Approach. So Professor Yuke Zhu.
Thank you very much for the introduction. Yeah, you can begin. All right, we have seen a wonderful talk of how HPC can be used for scientific discovery, right? So today I'm going to talk about robotics. When you think about robotics, maybe the first impression is all the gears and motors, all the sensors to actuators, right? Like the mechanical hardware aspects of robotics. But over the years, we see that the software aspects, like the brain part of robot, is as important as building the hardware, the mechanics themselves. Increasingly, we have seen that data-driven methods and computational-heavy techniques has been heavily used, to enable us to build the brains part of the robots. So that's kind of our goal. As a introduction said, that I've been leading these two research teams, both at UT Austin and NVIDIA Research, and both teams share the same mission, that's building general-purpose robot autonomy in the wild. And throughout the years, we work on a variety of robotic platforms, from robot dogs to quadcopters, and all the way to the cars. And recently, we converged on this unified research platform as humanoid robots, right? So these are robots with 2 legs, 2 arms, 5-finger hands. So they share human-like physics, and that makes them well-suited to deploy in human-centered environment. So if you look at the progress in the robotics community, right? So over the years, I think we made tremendous progress in building specialist robotic systems, and now we see that these systems like dogs or robot hands or quadcopters, robot arms, they have shown amazing, sometimes even human-level performance in performing tasks in narrow domains. But still, we are far from the dream of having the kind of general-purpose robot deploying in the wild home, household environment, right? So I call this kind of a general-purpose robot as a specializing generalist. But that I mean that they're not just jack of all trade, master of none, but instead they have a set of core competencies, but they're always learning to acquire deep expertise in new domains to learn how to learn to perform new tasks. So on our way towards this kind of general-purpose robot autonomy, I argue that we need to build something called generalist robot models, right? So these models are trained on massive data sources. This is where HPC comes in the picture to enable us to process a huge amount of data to be able to learn this kind of generalist model, sometimes it's referred to as the foundation model. And then with this a generalist model, that we can adapt that to enable more capable kind of specialized solutions. I see this kind of a trend going from a specialist to a generalist approach, and then specializing this generalist to be a better specialist that reflects a common pattern of technological advancement throughout the history. Let's just take the steam machine as an example, right? So the earlier version of a steam-powered machines, they were purpose-built solutions that only work in very narrow conditions. So they were really if you look at the history, they were developed in different civilizations across many, many centuries. And then the hallmark moment happens in 1764 when James Watt, and he made some important improvement over previous design. So if we look back in history, right, so his design was by no means revolutionary, but it is general and good enough to deploy in a variety of settings. So people start to put it in automobiles and to put it in cars and to put it in factories. And that widespread deployment of steam engine become the hallmark moments for the first industrial revolution. And from there, so new industry were created and many new technical problems to be solved. So, and that leads to a kind of paradigm shift of understanding of different energy sources and accelerate like the further development of new energy solutions, right? So now we have much better specialist solutions that we build for cars, for ships, for airplanes that do not look like the original OG steam engine, but they each have this like a specialist solution. Each have their own kind of complementary strengths for their own problem domains. And we see that the history repeats itself like in the kind of different fields of artificial intelligence, and particularly natural language processing. If you look like so how the kind of like natural language processing technology developed over the years, it started with some specific problem, like so text parsing. We parse English sentences into tree structures. We can kind of summarize a long text into shorter paragraph, and we can extract their sentiments or like so extract important information from the long text. And then in the past few years, we see the dramatic development of something called a large language model, like so exemplified by ChatGPT, right? So these are a new emerging paradigm of building kind of generalist NLP models by training on massive internet-scale text data. So this language model are not to train for a specific task. They are not tailored towards solving a particular problem. But what they have is a general understanding of human knowledge and human language and the word knowledge. And then as a result, we can actually use them as a backbone to solve a variety of language processing, language understanding problem, right? So we can use it to write poems like a Japanese haiku. It can like be a coding assistant to auto-complete your source code, or you can use it like to give a suggestion for your next travel plan, your next vacation, right? So if you think about solving any of this particular problem from scratch, it's incredibly hard to build like a domain-specific solutions from ground up. But by building this generalist language model first, that allows us to create much better specialist solutions and more quickly and more efficiently. So ChatGPT represents this family of AI models and foundation model called large language model, which have revolutionized like different fields of AI, particularly in kind of natural language processing. So if we kind of analyze the success recipe for how this large language model are built, so I think it really comes from the trinity of three key elements, right? So we have the powerful algorithm, like transformer models that's very expressive, was able to kind of process and encode a large amount of information, and then that we can scale them to like a billion or even trillions of parameters and scale with large-scale compute platforms. And also, we have access to massive training data. Like, for example, for language model, we have the entire internet, like Wikipedia pages, like GitHub source code, and all the text information you can get from the internet to funnel into the foundation model training. And the last is the accelerated computing hardware, like a GPU platform, right? So they're being able to offer like trillions, like a petaflops of like a computing power that allows like to quickly process like a huge amount of data and in order to train this billion parameter models. So naturally, we're asking, right? So seeing the success recipe of large language model, can we draw parallels to build the kind of like a generalist robotic models following the same recipe? So I argue that well, there's a lot of similarities that can inspire us like to see how to apply this kind of data-centric and computational approach to build robotic foundation model. But robotics does bring some unique challenges, right? So first, we have yet to figure out what is the right model, the algorithm, like the architecture that scales, unlike language model that only does kind of semantic reasoning in the text space at the high level. So robotics are all about like perceiving and acting in the here and now, right? So we need to actually process like a high-dimensional raw sensor data and a high frequency and determines like how to react in a closed loop, like at high frequency. And then there's not an internet for robotics data. That means that we cannot simply download robot control from the internet, right? So that means we need to be a bit creative to think about what are the data sources available? How do we find this kind of internet scale data in order to power the kind of training of the robotic foundation model? And the last, the robotics is a physics agent, right? So it's not just the computing hardware that we train the model. At the end of the day, it needs to be deployed on a physical robot. So the kind of physical embodiment of the robot platform also determines this capability envelope, right? So if we work on robot dogs, at best we can do dog-level intelligence. So that's why we kind of like converge on this kind of humanoid platform, because like they really allows us to have the capability, the versatility to perform a wide range of tasks in human-centered environments, and so that we can train a model that be able to carry out like a wide range of tasks in the wild. So motivated by the promise of like humanoid robotics, right? So we found this gear team at NVIDIA Research. So this team is co-led by me and my long-term collaborator Jim Fan. So if you look closely, you're gonna find both me and him like so in this video. So we don't build our own robotic hardware from scratch, right? So, but rather that our goal is to work with partners and colleagues from the robotics ecosystem to build AI brains for general purpose robot, particularly for this humanoid robot platforms. And the flagship project from our team is called the Project Groot. So that is an initiative to build like a general purpose multi-model foundation model for humanoid robots. So our goal is to build not only the foundation model as a single artifact, but to build an entire infrastructure and computing platform and the simulation tools and to support the training, the evaluation, and deployment of foundation model. That involves like the data pipeline, as shown on the left, the simulation framework for us to train and evaluate our model, and all the way to robotic deployment with the edge GPUs, like so that like to enable this kind of foundation model building, and NVIDIA creates like this 3 computer solutions to this problem, right? So we have trained our model on a supercomputer that's like NVIDIA DGX machine that's powerful enough to allow us to train that kind of a billion or even trillion parameter foundation models and fine-tune them with like a accelerated computing. And after that, we further kind of like run the simulations on OVX, so that is our simulation cloud servers, and that allows us to further improve the performance of the foundation model in simulation, evaluate before like so the real-world deployment. And after the model is trained, we develop like a third computer that's a runtime computer, right? So that offers the compact and on-demand computing that we can deploy directly on board on the physical hardware of the robots to be able to run inference in real time. Okay, so with the humanoid robots and also the 3 computers that we built at NVIDIA, so our team mainly focused on developing the core algorithm and the data pipeline in order to kind of enable and accelerate the foundation model development. Right? So for the algorithm part, and I think over the years we developed this overarching research principle that is to treat robotic engineering time with data and then compute, right? So if you look at the status quo, like so how robotic systems are built, there's a lot of the cost goes into manual engineering and system integration, mostly done by robotics engineers in the industry, right? So they've been kind of spending a significant amount of time crafting like more like a bespoke domain-specific solutions, and they spend a lot of time writing very detailed code or like so manually optimize the entire system. So I think that in our new approach, which I see as a data-centric approach, that we start to look into how do we leverage compute, simulation, and large-scale data sources to automate the process to build this kind of robotic foundation model, leverage general machine learning and AI technologies, and to significantly allows us to build like a generalist solutions, like faster and also more efficiently. So how do we operationalize this idea? As I said, that like one of the unique challenge for robotics is like there's not internet of robotic behavior or robotic control that we can directly download and then funnel into the model training, right? So about 2 years ago, I introduced a concept called data pyramid. Essentially, we just scout around and to see what are the kind of heterogeneous form of data sitting around that are available for us to use for training our robotic foundation model. Of course, at the bottom, we still have the internet data, right? So like all the YouTube videos, like internet tags, so they are massive in scale, and many of them are human-centered, right? So a lot of online videos shows like a human doing kind of activities. So if we can tap into these data sources, so they will offer us a huge amount of data for us to learn. But the challenge here, they are quite multimodal, and a lot of them are very unstructured. But in recent years, especially I would say like in 2024, we see, I call it as a Cambrian explosion of like this vision language model. So these are like the multi-model foundation model trained on this kind of massive internet data sources. So this have offers us as a backbone to build a kind of cognitive layers for the robotics autonomy stack, so that allows us to do like a high-level planning and reasoning based on the current sensory observation to determine what are the next subtasks to do and what are the kind of like situations like the robot is in. So one convincing showcase of using this kind of vision language model as a kind of cognitive modules for robotics stack is our original work called Bumble, which we introduced a unified VLM-based approach for like integrated open world perception, a wide range of sensor motor skills, as well as like a dual layer, like a memory architecture to be able to deploy on a mobile manipulator and to be able to perform this building-wide, like a mobile manipulation task in this kind of natural environment. So what it does is to let this kind of vision language model serve as, if you will, the operating system of the autonomy stack, and it calls like the perception module and the motor module as the through AP calls, and also save the past experience in some kind of memory system so that you can reason about a novel situation and leveraging the past experience. And so with that, as you can see, the robot was able to kind of reason about different situations and leveraging the reasoning core capabilities offered by the VLM models, and then to determine which skill to execute and also its corresponding skill parameters. So that allows us to scale for the very long-term autonomy that execute long horizon tasks, navigate a corridor, call elevators to go up and down in a building, and to retrieve the object and then deliver that to the target human. So we have seen that this kind of VLM models was quite capable to achieve this kind of systematic generalization on the cognitive levels. But the real challenge here is so as we move down to the sensor motor space, how do you actually integrate with the here and now to actually perform this a dexterous manipulation skill with the robot? That's still incredibly hard. So for that, we have been looking into the top two layers of the data pyramid, the synthetic data. How do we leverage a simulation, graphics rendering, all this kind of synthetic data generation tools to develop a large amount of data sets? Well, you might argue that if we have HPC, if we have enough compute, right, in theory, we can generate infinite amount of synthetic data. But in reality, right, so simulation and synthetic data is only as useful as how they faithfully reflect the real world, right? So, and there's content creation challenges, how do we actually orchestrate the simulation that mimic the real world environment? And some of the physical phenomena are still incredibly hard to simulate, that involve liquid or smoke and other things. So we still need some real-world data to close the simulation to reality gap, right? So these are the data that we can directly collect from the real-world hardware in the real world. So the nice property of this real-world data is if we manage to collect such data, learning becomes easy, right? So we can directly apply AI and machine learning models to directly learn from this real robot data. There's no embodiment gap. The model we learn from data sources can be directly deployed to a real robot. But the challenge here is they're quite expensive and costly to collect, right? So there's only a limited amount of data we can collect in the real world. So our idea or our philosophy is rather than picking size, picking our favorite across the three layers of a hierarchy, why don't we find ways to learn across them, or so to leverage all these heterogeneous data sources all together to build our robot autonomy stack, to build a generalist robot model that we envision. So let's look at the top of the data pyramid, which is the real robot data. So usually in robotics, it's done by teleoperation, meaning that there's a human that physically guide the motion of the robot through some kind of input-output devices. So this is a system that we developed at NVIDIA that we use Apple Vision Pro to track the human hand. The human hand got mapped to the robotics hand to perform a real-world bimanual manipulation task, like picking the mark and putting that in the shelf. Right? So you might wonder that if we have a way to scale these data sources to millions or billions of trajectories, so we will have that kind of internet-scale data sets to be able to train our foundation model. But the challenge here is all the logistics and economic questions, how do we actually get to that scale? So I think it remains an open debate in the robotics community, so how much we can rely on the real-world data only, or shall we even try to leverage synthetic data? So for us, it is a bit unclear, right? So how much real robot data will be sufficient for us to get kind of a true generalization to build, in order to build our foundation model. And also, the amount of data available is only linear with respect to the time, the money, the human resources that we put in, right? So to collect the data. Instead of just completely only relying on real-world data, we kind of making our bet on synthetic data, right? So the nice thing about synthetic data is once the simulation is built, that we can vary different axes of variations to generate exponentially many data points that significantly augment the amount of data available for us to train our robotics model. But there's a catch here. There's a downside of using simulation and synthetic data, is that building simulators are still incredibly hard, right? So traditionally, it requires a lot of engineering and the domain knowledge in order to orchestrate the thing that makes them look realistic and the robot behave realistic. So we're only limited on some restricted setting, say small tabletops or small scale environments. What changed the equation is the recent advancement of generative AI tools, right? So that really allows us to use artificial intelligence models to be able to generate this kind of large-scale, realistic, diverse environment automatically using learned machine learning models. So this shows a robot Casa, which is our recent work that investigates how to use the generative AI technologies to build this kind of realistic human-centered environment with a three-stage pipeline going from the 3D assets to environment building to task specification and task definition. So just to show you kind of how the three steps look like, so we use the text to 3D models to create a 3D asset that does not look good, but also they have the physical property to be simulated properly with the physics engine. And once we have the assets, we place them, arrange them in some kind of environments so that follow the natural statistic of how real-world thing looks like. So here we use some kind of interior design websites and the magazines like Architectural Digest and to get kind of the priors and templates that allows us to procedurally generate a variety of thousands of different kitchen environments that follow the realistic layout of a real-world kitchen. And after that, we use a large language model to propose human activities and suggest what one task to do based on the objects and also the appliance and the scene layouts and in the environments that give us hundreds of thousands of different tasks that we can do in the synthesized environments. And with this kind of robot Casa environment, that serves as this kind of a simulation runtime, simulation sandbox to be able to develop this basic foundation robotic skills involved pick and place objects and manipulating articulate objects opening doors, twisting knobs and opening microwaves, pressing buttons, right? So we've been using this simulation to train this kind of foundation skills as the basic building blocks and to scale for longer term robot autonomy. So not only that we have a simulation environment, we also need to generate the behavior data, the action data, to funnel into our foundation model training. So that leads to the sister project called Dex Mimicsion, which is the automated data generation pipeline. So the idea is quite simple, right? So we go from a limited set of a human demonstration, say 5 human demonstrations you can quickly collect in 10 minutes of time, and then we leverage computations to multiply the number of trajectories in simulation. So you can go from very small set of human demonstration, like 5, to quickly thousands of demonstrations that you can synthesize in simulation. The ability to be able to multiply the trajectories is based on the idea of that we can simply replay the trajectories in simulation in this kind of synthetic sandbox environments, but adapt that trajectory and morph the trajectory to the new location based on the mark placement. Right? So you see on the left, you see that's the source human demonstration from our data sets. On the right, you can kind of transform the trajectory to pick up the mark in a new location. And if you look at compare between these two images, right? So the relative pose of the robot gripper and the mug doesn't really change before and after. What's changed is now that you actually move the gripper to the new location to pick up the mug. So with this, we can kind of synthesize and many different trajectories. Of course, not all trajectory will be successful after the transformation, but as long as you leverage compute to generate a huge amount of data, and we keep the successful ones as augmented data sets for training. And this is concretely how we implement the DEX imaging pipeline. We kind of segment the trajectory with object-centric states and into different subtasks, and then we kind of build the state machines to transit between different modes of coordination between the two arms of the humanoid robots, and then with that we can replay the trajectories and then synthesize a lot more data. And these methods can be applied to a variety of different embodiments, right? So we try that on two robot arms and with a parallel jaw gripper. It can apply to our humanoid robots. It can be applied to long horizon tasks that involve many different objects. All of these are completely simulated and that's ultimately generated in simulation, leverage large-scale compute. Right? So with the generated trajectories, we show that so that can significantly lower the data requirements for training real robotic system. Right? So we can collect a handful of trajectories using teleoperation with a robot, and then we synthetically generate a huge amount of simulation data using DEX imaging pipeline, and then train on this combined data set, deploy back to the real robot to achieve that kind of robustness when kind of operating a trained vision-based manipulation policy for performing this task. And also we show that as we crank up the amount of data available using DEX imaging pipeline, so going from 50 human demonstrations to 100 generated trajectories, 300 to 3,000, we see a steady increase in the robustness and generalization of the trained model, right? So, and with the 3,000 generated trajectories, that we got 65% increase in the performance. Again, so treating the kind of engineering and researchers' time with compute and data, so we're able to significantly improve the robustness and generalization of the model using computation tools. And also we show that we can actually learn across the data pyramid, right? So by combining the real robot data with simulation together, and we can co-train them in a combined data sets that also in turn improve the robustness and generalization in the real robot execution. So this is one example that we show. What if you only train with 50 human demonstrations and you only get a 13% success rate, but if you co-train with a large amount of simulation data that you can almost get for free, that almost double the success rate. Of course, this is still quite challenging task because a deployment environment, you never seen the objects, and so we still need to improve the the diversity of the synthetic data to push the performance further. All right, so that's what I talk about the data pyramid, right? So that allows us to bootstrap the robot autonomy by combining these different data sources together from real-world data, synthetic data, and the web data together. But if you ask me, so how much data, how much compute is sufficient for us to train that kind of truly human-level generalist robots, I would say that maybe it's never enough, right? Because as the name suggested, it's a generalist robot inevitably will encounter new situations and they will be requested to perform new tasks in human environments. So we have to kind of have a way to make them collect new data and learn continually as they deploy, right? So we cannot build a perfect robot autonomy in lab settings. We need to kind of deploy them in the wild and let them learn from real-world environment. So for this, we kind of need a new mechanism to build a data engine so that we can deploy robots and then let them produce like a massive amount of training data from the kind of a deployment environment for learning. So to discuss the data engine, and let's kind of revisit like the training procedure for large language model, how ChatGPT is built, right? So the training actually involves 3 key stages. And the first one is called pre-training. That means you use self-supervised learning objective to train on unlabeled internet-scale text data to build a backbone. And usually you use like trillions of tokens from the internet to train the model. And after that, you fine-tune the model with the high-quality question-answer pairs, so that so because it's high-quality human-annotated data, that you start to align the model to make it to generate like so high-quality responses like based on human questions. And after that, there's a last step called RLHF, which stands for reinforcement learning from human feedback, right? So you let the model like generate different answers, and then like so you use like human preference to align the model towards a more preferred responses. So drawing the parallel here, to build a robotics foundation model, we argue that it's likely it's going to follow this 3-phase approach, like the large language model, that we pre-train on the data pyramid, as I showed earlier in the last session. And then after that, we can fine-tune that with domain-specific data, see that we can calculate domain-specific trajectories using human tally operation or other mechanisms, and fine-tune that backbone and with like that kind of domain-specific for that specific task. Then after that, we need to deploy and then kind of like finish the alignment to ensure that kind of like the safety guarantees and like so keep pushing the performance envelope like so in the deployment environment. So one of the central idea for building the data engine is called the robot learning data flywheel. So that essentially characterizes the virtuous cycle between the robot deployment and the model update, right? So let me show you here. And we have more data, so we can leverage AI and machine learning models to build a better model. And this model, when they deploy to robots, will lead to more capable robot system. And this more capable robot system will lead to the increased deployment of the robotic hardware in real-world tasks. And then the increased deployment will in turn increase like the training data available for us to train the next version of the model. So you just from there you can have the kind of positive reinforcement loop, right? So more deployment leads to better model and so on and so forth. But the challenge here is like we need to solve 2 things to enable this data flywheel. One is like how do we ensure the trustworthy deployment? The robot will not be perfect from day one, right? So there needs to be some guardrail and safety mechanism to make sure that like so there's no catastrophic failures before the robot reach like perfection. The second is like as we turn the data flywheel, there's a huge amount of data generated from the deployment environment. How can we learn kind of continually and effectively with the kind of petabytes or sometimes even more like data that we collected from the deployment environment? So to investigate these questions, like so about 2-3 years ago, we started building this series framework where we kind of enabled robots to learn on the job. So here, we assume there's a human and robots, they collaborate together through some shared autonomy setup that because like so they share like the control of the system, like so the robot does the bulk of the task, but like when there's like corner cases and difficult situations, the human can step in and take over and then kind of like cover the difficult situations, like handle the difficult situation. But not only this is like a shared autonomy system, so this is also a data engine, right? So all the kind of like experience from the human robot team will be saved to a centralized memory storage, and that serve as the training set for us to update the model for the next iteration. So we can train the model from the kind of aggregated data sets throughout the beginning of the beginning of the deployments and all the way to now, and then train the next version of the policy, then get deployed to the robotics back. So this video kind of give you a concrete example of how the system works through human-robot teaming. So at the beginning, the robot runs its policy autonomously. So at some point, the robot gets stuck and asks for help. So this is achieved by some model-based runtime monitoring algorithms through some uncertainty quantification. And here, now the human needs decide to step in and kind of provide action feedback, interventions. And then once they recover, from the bottleneck stakes, and the robot takes over to complete the rest of the task autonomously. So as we kind of deploy these systems of a human-robot team, we show that over rounds and rounds of a model update and deployments, the amount of human workload decrease as the robot policy improves, right? The robot level of autonomy increase. So we visualize the human interventions distribution in this task in the round 1 and round 3 of deployment. We see that in round 1 deployment, that's the initial phase. So the robot gets into difficult situations pretty frequently, right? So there's a pretty frequent human interventions, so the human needs to step in, take over control, and correct the mistakes. But as we go to the round 3, the later stage of deployments, and the robot runs autonomously most of the time. So the amount of human engagement will gradually reduce as as we push the level of autonomy of the robotic system. So in our kind of latest work, we kind of extend this series framework to fleet control settings. So now, not only it's one human controlling one robot, but rather the human can supervise a fleet of robots deploying in a variety of settings. So to be able to do that, what the core is to train a world model that can predict a future from the past observation. So the world model can anticipate the imminent failures and use some uncertainty quantification and risk assessment technologies to pause the robot execution when things go wrong, and then ask human to come and help. So this animations illustrate the idea, right? So we have this kind of 9 robots deployed in different kitchen environments, and they are tasked with performing a variety of household activities. And zooming in as an example, you see that the robot is about to knock off the juice box, and using the visual world model, it can hallucinate how the future looks like if we continue to evolve and continue to proceed the actions. And you see that the juice box might get knocked over. And then so the robot stop here, ask the human to intervene and provide the corrections and to pick up the juice box successfully and place that in the mug. And then so we hand over control to the robots to kind of proceed with the remaining part of the task. And then you can kind of run this kind of fleet control settings with a human to ensure high level of success across many different tasks. And all the experience from the fleet of a robot will contribute back to the data storage, and that serve as the training data to update our models for the next stage of deployment. Okay, so with this kind of system, so we showed that so both the performance of the combined human-robot team and also the autonomous policy improves. More importantly, is that as we increase the level of autonomy for robotics and the amount of a human efforts and the human time will gradually reduce, right? So we're more and more relying on the autonomous execution of the robot and less with the manual labors and on the supervisory feedback of the humans. So that kind of shows the two key ideas in our data-centric approach to build the robot autonomy with a generalist robot model, right? So the first is the data pyramid that I talk so how do we bootstrap the base models and by leveraging all these kind of different data sources combined from real-world data, synthetic data, and web data. And what we envision is so as we keep developing the generative AI technology, as we turn the data flywheel by deploying robots in real-world environments, so the amount of synthetic data and real-world data will eventually dwarf the amount of web data available, and more as we leverage generative AI tools, as we kind of achieve the widespread deployment of intelligent robots, we're going to rely more and more with the top 2 layers of a data pyramid to kind of continue push the capability envelope of our robotic systems. So just to kind of conclude here, and there's 3 kind of research principles that I covered in today's talk. So the first is our top-down approach to achieve robot autonomy, right? So we want to, rather than kind of build a specialist solutions one by one and gradually expand the level of autonomy, we want to first build this generalist robot model as a centralized approach, and then with the hope that after we build this generalist model, and this generalist approach allows us to build better specialist solutions. And for that, because robotics are embodied agents, so we choose to use humanoid as a versatile hardware platform to study our research questions. The second principle is learn across the data pyramid, where I talk about how do we leverage heterogeneous data sources to significantly augment the amount of data available compared to only relying on real robot data. And the third, I argue that the first initial deployment of robotic system in the world will likely not going to be a fully autonomous solutions, right? So for that, we need guardrails, we need a human-robot partnership in order to achieve that kind of a trustworthy and safe deployments in the world. And from there, not only is a shared autonomy system, it's also a data flywheel that allows us to continually gather huge amount of training data to keep improving our robotic system in continual lifelong learning settings. So with that, just to echo the overall kind of theme of the conference, right? So in the past decades, we already see that accelerated computing hardware like GPUs and power a variety of AI applications by kind of enabling computers to process large amount of data and carry out very complex calculations and quickly and efficiently with modern neural networks in particular. So we have seen that how data and compute enables transformative technologies in the digital space and to process large amount of text and visual data, especially with the emerging paradigm, what we call foundation models. So our mission is to kind of build a computing platform, the simulation frameworks, as well as the fundamental algorithms to enable a similar technological revolutions in the physical space, and now with humanoid robots and general purpose robot models in particular. So with that, I'm gonna end here and thank all my student and collaborators and contribute to the work I talked about today. Thank you.
Thank you, Yuke, for that great talk. We have a couple of minutes for a few questions. If there are any, there are these microphones in the aisles. So we'll start here.
Hello, my name is Diego Roa, University of Delaware, Argonne National Laboratory. Thank you for your talk, very interesting. My question is, AI is not perfect yet. There's still some error, even if it's 99% perfect, it's not perfect yet. How do you guarantee that you keep the correctness in the critical tasks? And in your experience, how important is that in the whole ecosystem of robotics?
Sorry, I now hear your question very clearly. So yeah, talk about the correctness.
Okay, so even if AI is not perfect and there is still some error, how can you guarantee the correctness in the critical tasks? And in your own experience, how important is that for the robotics in the whole ecosystem?
Got it. So you're saying especially for the mission's critical task, how do you ensure the correctness of the method? Is that the question?
Yes. Yes.
Okay. Yeah. Perfect. Yeah. So that's why I said that we see that simulation plays actually two key roles in the entire workflow for building the foundation model. The first is as a training source, right? So we provide some examples how do we use synthetic data simulation for training that foundation models and using the data pyramid and using the co-training techniques that I introduced. But also, I think another very important role is for evaluation and the systematic validation of the model before real-world rollout and before real-world deployment. The nice thing about simulation is so you can actually orchestrate the environments to change the different configurations easily, so that we can have a systematic understanding of that model performance before we roll out in the real world. And ultimately, real-world validation is still going to be the golden ruler, right? So it's still going to be the ground truth for us to ultimately judge the performance of the robotic system. But simulation, especially as we make an advancement in making the simulation more realistic and more diverse, that provides a very nice a sandbox that allows to systematically benchmark and evaluate the performance and before the real-world deployment.
Thank you.
Yeah.
Thank you. We have another question here. Yeah.
See if I can. Oh, okay. Hi, my name is Nate. I'm from Seattle University. I'm very interested in, so this is a very forward-thinking question, how we can ensure that autonomous agents, be them robots or chatbots even, behave ethically. And a lot of your examples seem to be caregiver robots. So I was wondering, going to the example of Bob with the soda, for example, what if Bob has a dietary restriction? Bob shouldn't have soda, right? Or what if Bob requested a substance that was illegal or bad for him health-wise? Should the robot comply, right? And we can think of a lot of other generalized specialist robots, such as in law enforcement, that would face a whole bunch of ethical dilemmas. So thinking a little bit farther into the future, how do you think we can address those problems of ensuring not just correctness in terms of action, but correctness in terms of ethical behavior?
This is like fantastic question. I think this is like to be able to deploy robotic system goes way beyond just a technological question, but also like so it should involve like so cross-discipline dialogues in like on the legal side and also on the kind of actually safety aspects, like so and also kind of like a regulation aspects. I think so. A lot of the discussion is still quite nascent, it's still early stage, like, but we do need to seriously kind of like pay attention to some of the other aspects, non-technical aspect of the equation. So as we continue to use more and more AI technologies, we're gonna see a lot of challenges, right? So in the safety aspects, because like I mentioned, like so in my talk that we use like a vision language model as a cognitive layers, and then at the low level you also need to actually learn how to perform tasks like by driving the motion of the robot. So the robotic foundation model will inherit all the challenge from like LLM, VLM, so all the kind of like hallucination problems, like so all the kind of like misalignment problems. So I think like so we need to kind of like draw insights like how to actually solve them, like so like from that community. But in additionally, so there are also even more technical challenges because like so the physical world is just like less forgiving compared to the digital world, right? So and if the humanoid is really kind of like a 50 kilo, 100 kilo heavy, if you fall to the human, it's going to be a human nutcracker, right? So and all the kind of functional safety aspects are going to be super critical. So that leads to a lot of system challenges, not only just to build the AI part also, but to build all the kind of well-disciplined engineering. For example, like we want to have redundancies in the system. If the kind of the main controller fails, like there should be a fail-safe. There should be redundancies baking in the system. We should have some kind of way to certify our human detectors and the controllers so that like so there's no even if like there are some failures might occur, but there's not going to be catastrophic failures, like especially when we deploy in the human world. Back to the kind of like discussions on what's the principles. I think there's also a field called like a constitutional AI that essentially kind of like determines what kind of like the right high-level principles that we like inspired by osmosis free law for robotics, but by no means that's enough, right? So when we actually can like talk about real-world deployment, so yeah, I think these are the like, very good open questions to explore. So in addition to the technical questions that we're investigating. Yeah.
Okay, we'll take one last question. We are running out of time here. Just
Okay,
final question.
Jose Monsalve from AMD. Thank you very much for the talk. I have a really quick one. So there is all these opportunities for multi-agent LLM-based models or generative models, but I was wondering what other opportunities there are for other type of models, especially for the digital twins. I don't know if, let's say that we are evaluating a task that is opening a door. Do I have to find mechanisms within the digital twin to be able to have sensors for the door opening, or do I create models on top of that that analyze the vision, the result of the simulation to see if the door is open or closed? So kind of like these multiple other mechanisms that may exist in terms of AI, where else can models exist and what other models can be applied to this?
Yeah, yeah. So I think so. You're talking like so simulation, like so how realistic it needs to be. Do we need to simulate all the kind of like nitty-gritties of like the dynamics like in order for it to be useful, or like so like if we want to learn the door, all we need to know is like maybe like some kind of high-level understanding whether the door will be open or not, like so by taking this action, right? So just like the famous quote by George Box, right? So almost around some are useful, right? So like simulation is just yet another approximation of the real world. And so it depends like so the kind of like so the level of reasoning you want to do. Like if you want to do high-level planning and the reasoning, like so like how do I move around, like to in order to reach the door and like to enter that next room. Probably you just need a reduced model, reduced simulations, but you want to actually kind of get down to the actual execution of like a contact-rich interaction with the door, and then you will need like a more high-fidelity digital twins, right? So I think so. Like the kind of granularity and the fidelity we need is kind of like task dependent and also situation dependent. It really kind of depends like what kind of level of reason you need to fulfill the goal. Our hope is like you don't really need to simulate all the way down to the kind of like a lowest level mechanics, right? So, but like so to adaptively determines the right level of abstraction to build that model so that we can trade off both the efficiency as like the fidelity needed to carry out and the training and the evaluation. Yeah.
Okay. Well, thank you very much. Well, that brings us to the end of this invited session. Again, thanks, Yuke. And again, please join me in thanking both Anna and Yuke. And enjoy the rest of your stay here in Atlanta and the SC24 conference. Thank you.